In this video, we'll compare the two different approaches we have for hypothesis testing when you know the population standard deviation. We'll look at critical value and we'll look at p-value, right? And we'll compare them. They actually start almost the same way. And that is the two key things you're going to need to do are figure out what the hypothesis is and find that test statistic. It's after that that the two different versions come through. So if you're one of these people that are not sure, you want to make a decision at the last minute, maybe you're the person that drives on the highway and you can't decide if you want to get off on the exit, so you're driving through those white zebra stripe lines because you can't decide if you want to stay on the highway or exit. Well, that's okay because you had a little time to make that decision, but eventually you are going to have to decide. So the first thing is you got to write out that hypothesis statement so that you know whether you're doing a test that's two-tailed, left-tailed, or right-tailed. The significance level you generally don't have to decide on because they've given you the significance level. You will have to compute that test statistic. So sample mean over minus the population mean over population standard deviation divided by square root of the sample size. So that is your test statistic. Once you have that, now you're going to have to make the choice. So on the left side of this, and I think I grabbed this from the textbook, the left side is the critical value approach. Okay, so on the critical value approach, you take that test statistic and use that as sort of your boundary, and then you calculate the critical value based on the significance level. So if it's two-tailed, you got to take the significance level and divide it by 2. Otherwise, you find your z alphas. Then you compare, right? So you decide whether to reject or not reject. So if those test statistics show up either far to the left or far to the right of that critical value, then you reject the null. If it's somewhere on the inside, then you do not reject. And then, of course, at the end, you got to write up your summary statement. If you're doing the p-value approach, you take that z-score that you found before and look in the area chart to find the area either to the left or to the right of that z-score, depending on what type of test you're doing, and then compare that to the significance level. So you're not finding any z-values based on the significance level. You're using that significance level to compare it to the p-value to decide whether to reject or not reject. So if the p-value is less than the significance level, reject the null, otherwise do not reject. And then, of course, at the end, interpret your results. What does this mean that I found p-value of whatever and compare that to a significance level? All right, so this one is sort of worked out already, but the problems you're going to see in the textbook in this section start out kind of like this. You're given the sample mean, you're given the number in the sample, you're given the population standard deviation, and they set up the hypothesis test for you. That the null hypothesis in this case is that the mean is 22. The alternative hypothesis is that the mean is less than 22. So this would be left-tailed. So the first thing is you're going to need that test statistic. So the test statistic is calculated over here. Sample mean minus the population mean over standard deviation over the square root of n. Right, when we do that, we come up with negative 1.414, and that's where the two versions differ. So if you get a z-score of negative 1.414, your significance level is 0.05, right? Because that was given. If you want to do this by the critical value approach, then the first thing you need to find is a z of 0.05. This is left-tailed, so I don't have to worry about dividing alpha by 2. I just need to figure out what z of 0.05 is. So I come over to my table. You realize at the bottom of those t-charts, and I realize this is sideways, but I'm not flipping it 3 times. We can read this sideways. Z of 0.05 is this guy right here, 1.645. But because we're on the left side, it's going to be negative. All right, so z of 0.05 is negative 1.645. The test statistic that I calculated is over here. So what does that mean? Do not reject. Do not reject the null. There's not enough evidence to favor the alternative hypothesis. All right, what if I want to do this with a p-value approach? So now I take my chart and I look for the area to the left of z equals negative 1.414. All right, so here's negative 1.40. Here's negative 1.41. Right? You notice the number I get is 0.0793. To two decimal places, I'm going to write that as 0.08. 0.08 is greater than 0.05. So my p-value is greater than my significance level. Remember, the significance level is the amount of error that I'm willing to accept. So I'm willing to accept up to a 5% error. That p-value is above that, right? That p-value is 0.08. So too much error for me to be comfortable rejecting the null. Do not reject the null. We better get the same answer both ways, right? So there shouldn't be any cases where the critical value gives you one answer and the p-value gives you another answer. These are just two approaches to get the same result from the problem. All right, let's take a look at number 2. Right, number 2 says find the test statistic p-value tested at the 5% significance level. So let's try this both ways. The mean is 23. The population mean is 22. This is a two-tailed test, because I'm simply saying that the mean differs from 22. I don't know whether it's above or below. So let's calculate that z-score. I end up with the sample mean minus the population mean over the standard deviation divided by the square root of 24. Right. I can see on the top I get 1. I just don't know what I get on the bottom. So I get 1 divided by, and then in parentheses, 4 divided by the square root of 24. 1.22. All right, so then using the critical value approach, you would then find z alpha over 2. Alpha over 2 because it's two-tailed. Take that 5% significance level and divide it in half. So half of 0.05 is 0.025. So now I go to my sideways table over here. Z of 0.025 is this one in the middle, 1.960. But because it's two-tailed, it's actually plus minus 1.960. So it could be up here at 1.960, or it could be down here at negative 1.960. Right, where's that test statistic lie? That 1.22 right over there. Do not reject. Right? Not enough evidence to say that I should reject the null in favor of the alternative. So right now I'm going to hang on to the null, not because I believe the null 100%, but simply because I don't have enough evidence to throw it away in favor of something else. All right, what does this look like if I were doing a p-value approach? So for a p-value approach, take that z equals, in fact, I'm going to do z equals negative 1.22 and find the area to the left of that. So negative 1.2012, I get 0.1112. But remember, that's the area on the left. This thing is two-tailed, so there's an area on the right that's equal to that. So the p-value is double that. Okay, so I found the value to the left of negative 1.22. That's a terrible normal distribution, even for a sketch. There we go. So I found the area to the left of negative 1.22. But because it's two-tailed, there's an area to the right of 1.22 also, which is the same. So my p-value actually comes out to be 0.2224, but at this point, does it really make a difference? Clearly, 0.22 is much bigger than 0.05. So that p-value is greater than alpha. So I'm willing to accept the 5% error. I have a 22% probability of an error, way too big. Do not reject. Now, in this case, you almost could have gotten away with not doubling it because the number was so big. But if you forget to do that for a two-tailed test, it could make a difference, right? If you had a p-value of 0.03, and 0.03 was on one side and you forgot to double it to get the 0.03 on the other side, that's going to make a difference because you should have gotten 0.06, instead you got 0.03, and now you've rejected when you should not have rejected. And now you actually have committed a type 1 error. All right. Let's try another one. Let's take a look at number 4. All right, this is a left-tailed test. How do I know? Because it says the alternative hypothesis is that the mean is less than 22. So first thing is, let's calculate that test statistic. Sample mean is 20. Population mean is 22. Standard deviation is 4. Number of items in the sample, 32. All right, that's going to give me a -2 on the top, divided by 4 over the square root of 32. That gives me -2.83. All right, critical value approach. Problem set at the 5% significance level. It's off the screen a little bit here, but I promise the problem said 5% significance level. So I'm going to find z of 0.05 as my critical value. I come over here, scroll down, z of 0.05 is 1.645. Because I'm doing left-tailed, I'm going to write it as -1.645. So that table only gives me positives, but remember I need to adjust if I'm looking on the other side. All right, draw yourself a little picture. Critical value, -1.645. Test statistic, here, -2.83, clearly in the reject spot. So reject the null, enough evidence in favor of the alternative hypothesis. All right, p-value approach, look for the area to the left of z equals -2.83. So I take my table of values, -2.80123. So 0.0023, that's a small number. All right, so that's 0.002. My significance level was 0.05. Clearly, p is less than alpha, right? If you have to line them up under each other to see what it is that you're looking for, line them up because it makes it a little bit easier to see. All right, so let's take a look at some application problems here. I'll pick a few out to do. There's a lot of words in some of these problems. So RDA is the recommended daily allowance. The recommended daily allowance of iron for females under age 51 is 18 milligrams per day. So this is going to be my mean. Sample of 45 adult females, so that's the number in my sample. That's n equals 45. They were selected. Their iron intake was monitored for 24 hours. 24 is nice, but it's not really part of the problem, at least what I need. They found a sample mean was 16.12, so that's my sample mean. Assume the population standard deviation is 4.2 milligrams at the 1% significance level. So this is pretty strict. Do the data suggest that adult females under age 51 are getting less than the RDA of 18? All right, so the null and the alternative hypothesis were written out for you. The null is that the mean is equal to 18, that they're actually getting the 18 milligrams they're supposed to. The alternative hypothesis is that it's less than 18. So that means that this test is left-tailed. All right, let's make a list of what I know. The mean is 18. Number in the sample is 45. Sample mean is 16.12. Population standard deviation 4.2. Significance level 1%. All right, so let's calculate the test statistic. Take the 16.12 minus 18 over the population standard deviation divided by the square root of 45. All right, so it looks like there's a little bit of a difference between what they're actually getting and what is recommended that they get. Is it enough, though, to reject the null hypothesis? That's our question. All right, so as I've been talking, I've been typing. I get a z-value of negative 3.00. Right, so using the critical value approach, I would find z of 0.01, but I would apply the negative to it because the test is left-tailed. So z of 0.01, 2.326, except it's negative 2.326. All right, so that critical value is my boundary. That test statistic over here is far enough out that I can say reject the null. If you want it with a p-value, then go on to that set of z-scores and look at negative 3.00. I get a value of 0.0013. The significance level that I want to take into account is 0.01. So yes, clearly p is less than alpha, so reject the null. I'm willing to accept up to a 1% error. The probability I'm given is essentially 1/10 of 1%. So yes, I got plenty of room to reject the null in favor of the alternative hypothesis. All right, let's try one or two more of these, and then we'll start to wrap it up. All right, so this is about cadmium, toxic to animals, found in mushrooms. Safety limits a half of a ppm, part per million. Researchers measured the level in a dozen edible mushrooms. Look, your sample size is hiding right in here. Sample size is 12. Some of the data was 6.31. That means I'm going to have to calculate my own sample mean. So the sum is 6.31. There were 12 items in the sample, so take 6.31 divided by 12. 0.526 if I round it to 3 decimal places. All right, so my null hypothesis is that the mean is actually equal to 0.5. The alternative hypothesis, it says, does it provide evidence that the mean level is greater than? So the mean is greater than 0.5 is my alternative hypothesis, which means that this test is right-tailed. All right, what else do I know? I know I can calculate my my test statistic, take the sample mean minus the population mean over the standard deviation, which is given down here, 0.37, over the square root of 12. I can see the numerator is going to be 0.026. I don't know what the denominator is off the top of my head, so let me run it through a calculator. I get 0.24. All right, so if you want to do this by the critical value approach, I want the 5% significance level. So let's find z of 0.05. Z of 0.05 is 1.645. positive because it's right-tailed, and so clearly that thing fits in the do not reject region. Right, 1.645 is over here. 0.24 is pretty close to the mean, so do not reject. All right, if you want to try this with that p-value approach, look on the chart at z equals 0.24, but I'm going to actually use z equals negative 0.24 because I want the area to the left, actually I want the area to the right of positive 0.24, so the area to the right of this is the same as the area to the left of that. And since the table gives it to me as area to the left, I'm going to be cheap and I'm going to go to the negative 0.24. 0, 1, 2, 3, 4, 0.4052. Well, that is way above what I'm willing to accept. So that P is way bigger than alpha. Do not reject. So if I were to write a conclusion to this, I would probably write some language like, at the 5% significance level, the data does not provide sufficient evidence that the mean level is greater than the government limit. I could also mention something about my p-value being about 41% and the significance level being 5%, therefore the p-value is well above the significance level. All right, so this is me staying at cheap hotels in Pennsylvania. Daily charge in dollars for 40 hotels and motels in Pennsylvania found to be $73.26. Okay, so that was a sample. The sample mean was $73.26. At the 10% significance level, so I'm willing to accept a little error in this one, does the data provide enough evidence to conclude that the mean charge for a hotel in Pennsylvania is more than $70 a night? So my mean is 70. I sampled 40 hotels, so that's my N. Assume a population standard deviation of $15. So the null hypothesis is that the average price of a hotel room in Pennsylvania, $70 a night. The alternative hypothesis, is that the mean is greater than 70, which means that this thing here is right-tailed. All right, let's take a look at a couple of examples, a couple of ways we can do this. We can do it with critical value or we can do it with p-value. Either way, we need that test statistic. So take the sample mean minus the population mean over the standard deviation over the divided by the square root of n. So on the top, I can see I get a 3.26 divided by 15 over the square root of 40. 1.37. All right, so now we can decide which method we're using, right? And this is at the 10% significance level. So if you're doing critical value, one-sided test, we can take z of 0.10. Right, that's the first one up here, that 1.282. Right-tailed test. Boundaries at 1.28. The test statistic that we calculated was 1.37. That's over here. So at the 10%, it's okay to reject the null. How about p-value? I'm going to look to the left of z equals negative 1.37 because that's the same as the right of z equals positive 1.37, right? You can take the area to the left of positive 1.37 and subtract it from 1, but why? So negative 1.301, 2, 3, 4, 5, 6, 7. I get 0.0853. All right, so even if I round it to the nearest hundredth, I get 0.09. My significance level was 0.10, so p is less than alpha, so I can reject the null. At the 10% significance level, there does seem to be enough evidence to reject the null in favor of the alternative hypothesis that the average price of a hotel room in Pennsylvania is more than $70 a night. And again, do you see the importance of the significance level? If this significance level was not 0.10, if this significance level here was, let's say, 5%, then instead of me saying reject the null, I would be saying do not reject the null, because that p-value of 0.09 is greater than 0.5. But if we're going to do it at the 10% significance level, then yep, we got enough. Reject the null in favor of the alternative hypothesis.